All right. 3, 2, 1.
That was
awkward.
Yeah. That was super awkward.
Okay, great. Hey, everybody. Welcome to Double E's Talk Tech. My name is Mike Hoffman.
And I'm Daniel Bogdanoff, and we're joined again by Stefan Loeffler, who is an optical guru. Don't tell me that you're not a guru, because this is the third episode in a row. You're definitely the guru. He's going to talk today. What are you going to talk about today?
Yeah, we'd like to talk about optical infrastructure and where optics is in the network, because we don't see it.
Yeah, well, we do see it, but it's Netflix.
Can we call it a laser-driven Netflix delivery system?
LDNDS.
Done.
LDNDS.
Oh, certainly.
Great.
That's a new acronym. I'll put that down.
We
Take that one to the symposium.
Yeah.
yeah, submit your paper at OFC next year. So you've used a term before in some of the other episodes. You referred to things as client side. Can you talk a little bit about client side and whatever the other side of that is?
Yeah, it's just a differentiation between on what side is the network that transports the signals, and on what side is the equipment that can be either a consumer or a business. So the client is the business, the network is the line side.
Okay. Network side, line
It's
side.
as simple as that. Yeah, but we were talking about fiber in different places of the network. And if you think of today's networks, mostly we don't see the fiber coming out of the wall. Most of us.
I don't, that's for sure.
Yeah. Certainly, if you woke up your desk and come by one of these little racks or cabinets, and if they have a transparent window in front of it and you see yellow, then it's fiber. That's typically what
like a yellow glow?
No, not a
Or
yellow
like
glow.
a
It's
yellow
just a yellow
cable.
yellow color for the cable. So like this one is black, it would be yellow.
Interesting. Okay.
Yeah.
I was picturing like a radiation glow or something. But
No.
technically, we're
can't
communicating using radiation, right?
Technically, yes, but it's an invisible, to us
The best
human
kind,
beings, invisible light.
Fair enough.
Yeah. So yeah, whenever I turn on my cell phone, it's actually using fiber, but after the first antenna. And that's one of the latest technologies, is getting fiber to the antenna. So one of the problems with installing antenna is that you have to have power at the antenna. And more recently, we're putting the power source down the pole, or even into what they call a small hotel, a hotel, so to say, for the transmitters and the line cards.
Okay. So I imagine they call it a hotel because there's a bunch of different...
Yeah, it's hosting multiple.
So you turn on your phone sends out a ping to a tower somewhere, and the tower has the base station hotel at the bottom.
Yes.
And then that connects
Right.
to the network, capital N.
Yeah, if it's has been installed a few years ago, then from the base station onwards, it will be fiber. If it's a really new one or an experimental one, you may even find the fiber running up the pole, running up the antenna. Now now we are in the backbone. So we have a network that can be star form, or it can be meshed, or it can be a ring. And
Can you talk about those a little bit? So star mesh ring. So yeah.
Yes. For example, base stations are often organized in star form because you reach out from this base station hotel to multiple antenna, to multiple cells, basically, or
Like a little repeater cell station is what you're, or is it a?
yeah,
I know okay.
Yeah. And then you're connecting into the next local office or central office. From here on, it's usually either mesh or ring. Rings are popular in metro infrastructures because you can encircle an entire area with fiber that is then going through local offices, where you can add and drop signals. And that's where we have this add-drop multiplexer.
So that's like a big, almost like a traffic circle for data.
You could consider it. Yeah, Munich has such a ring. So if you think of Munich, it has A96 going around the city, and then there are multiple connection stations where you go into the city or out of the city, and pretty much like that.
Okay.
You have a fiber ring where you have stations where you can add and drop signals, and these add-drop signals are one of the biggest buzzwords of the past OFCs and the past years in fiber optics.
Okay. So fun fact, the highways run north-south or end in a 5. So like we have I-25 going through town. And then highways that run east-west end in a 0. So 10, 20, 30, 40, 70. And then loops have an 8. So like Fort Worth, where I went to high school, had 820, which is a loop around the city.
Oh, okay. So like a prefix number.
Yeah.
Yeah.
And then there's 820, so it's like an I-20 based loop around the city.
Yeah.
Oh, interesting.
Yeah. So a little tip for you next time you're navigating around the U.S.
Yeah, it's always odds or north and south, evens, east and
5s,
west. Yeah.
Wow, that could have helped me so much. Why am I learning that now?
So you're just in Los Angeles. You had the 5 and the 105.
Yeah, I didn't see much of it. I was actually
that's a
buried
good
in
thing.
in
You're traveling at light speed in a ring around the city instead. Yeah.
So which ring topology is probably the most efficient as far as resources are concerned, right? You're using less fiber to connect a network in a ring than mesh or star. So is that the most common?
Is it more flexible in terms of serving data over custom distances?
The big advantage of ring is it has built-in resilience. So you were talking about going clockwise or anti-clockwise. So consider a ring that is broken at a certain point. Then you can go to all stations from all stations just by going the other direction, going one of the directions.
And if you miss your turn, you can just go around again.
Yeah, of course.
Okay.
So built-in resilience is one of the advantages of ring structures.
That makes sense.
Mesh structures do that too. So
At a cost, of course, right? 'Cause
at the
way
cost
more
of more
links.
fiber, yeah. But also at the gain of more bandwidth. So a ring is basically a backbone, and if the ring is exhaust, you can go the other way around. That's the only way. That's it.
By the way, if you're watching and you're not familiar with basic network topologies, star, ring, mesh, just do a quick Google search. It's pretty self-explanatory. It's just kind of how the networks
I
look.
can picture it. Yeah.
Yeah.
I had no idea, but I think now I'm at least a pseudo expert.
Yeah.
So mesh is like a grid, right?
Yeah, basically the connections, one is connected to all, generally. Like in a wireless mesh network, like one base station can communicate to all base stations or multiple.
Okay.
Where a ring is they're all organized in a circle, and a star is everyone
Ring one is
communicates to
engaged,
one
yeah.
like central station, so it's all in and out.
Okay. Cool.
Not as good from a safety standpoint, because if a link goes down, you're done, right?
Sure. Makes sense.
So
Yeah, that's why networks now are really networks with all these mesh structures.
Interesting.
Yeah, it's built into the word. One would expect that a network is by definition like a net, but it's not.
So how often is that infrastructure, and this is maybe way out of league for what you're used to working with, is the format of the network defined by the geography instead of just like, oh, I'd love to do that, but I don't have right of way over this farm or whatever it may be.
That can be a deciding factor. If you talk about ring topologies, they're mostly, as I said, in metropolitan areas. Campus networks are also ring networks. Campuses like academic campus, but also campuses that are like in this area here, where you have multiple businesses in the same campus style setup. Their right of way is not the big problem. It's built in.
Sure. Okay. And these businesses are more or less client side, right? And
Yes.
then
yeah.
they are subscribing to some network provider. I guess as I use the term, it's starting to make more sense for me, that has actually installed fiber or at least fiber from someone else.
And provides bandwidth. And you lease fiber typically, or you lease bandwidth.
Okay.
Leasing bandwidth is probably more common, but if you need a certain latency, a certain bandwidth or capacity, and you don't want to compromise on that, leasing fiber is a good way, because then you have control over the bandwidth and you have control over the path that a bit takes. If it's taking too many D-rods, you're adding latency. A great example is financial centers like stock exchanges. They're connected by direct connection. That's point-to-point, shortest distance, because every microsecond or nanosecond added to this communication actually translates into lost money.
Yeah, that makes sense.
If you can
Especially
react faster, then your automated trading works better.
Computer driven. So the faster it gets data and processes data, the sooner you can buy or sell.
Yeah, that's one of the cases for point-to-point links.
Interesting.
Now, from the infrastructure standpoint, we're talking about client side and server side, for example, communications to the channel. Now, this channel, we're talking about immense speeds of data transfer through the fiber.
Quantities, at least, yeah.
Right. Yeah, quantities of per second. Yeah, thank you. And so, what are the limitations of the hardware that is doing the sending and the receiving of that optical data? Like, is the optical faster than the electrical side that's able to understand it and read it?
On very short distances, no. And also, whatever we do on fiber, at some point it's electrical. We need to create light out of electrical pulses, optical pulses out of electrical pulses. There will be a tipping point, of course, where quantum computing and photon-computing comes into play, but this is way out.
We're going to try and do an episode on quantum computing. I'm pretty excited about that.
Let's wait a few years, yeah.
Well, even now, we have a guy out in Santa Rosa who's like the guy. So you can look forward to that one.
Sure, yeah.
Yeah. I don't know nothing about that either.
Yeah, I wonder if optical will, as it competes with copper, will it ever compete with silicon, like an optical computer? That'll be my prediction.
It will.
Edit that part out.
It will.
No, tough. You already used it up.
Now we're into silicon photonics.
It's a thing. Of course it's a thing. So, like you said, everything optical inherently has an electrical component.
At the moment, yes.
Because the optical side of it is just light through fiber.
Yes.
But
but you asked for the limiting factor. I mean, the brute force approach would be just put more transmitters, more receivers into it. The limiting factor will be the power supply. So at some point, we have the problem that we need to get a power plant next to each central office. And that doesn't make sense. So
it's hard for me to fathom that much power usage. Like, what is it being absorbed by?
If you go back into computer science, if you're up your CPU by a factor of 10, you're moving 10 times more load, more electrical energy per second.
Electrical information, I guess. Yeah. Okay.
And that's what happens in telecom equipment as well. So you're just pushing more bits and bytes through, whether they are optical, photons, or electrons. It's energy. And then we've spoken about these complex modulation schemes, QAM and PAM, that require a lot of post-processing. So your raw signal does not tell you anything. You have to use a DSP to decode it, to de-emphasize it, and so on. And to get back to the bare bits and bytes, you're spending additional energy.
Okay, that makes perfect sense. You were talking about, so for an exchange, there's a point-to-point network. One point is obviously the New York Stock Exchange or whatever it may be. What is the other point?
Could be London Stock Exchange.
So it's actually point-to-point is almost a client-to-client.
Well, in that special case, yeah. This is a great example because, to my knowledge, this was one of the first commercially installed 100 gigabit Ethernet, 100 gigabit links, not Ethernet. It was 100 gigabit.
Wow.
Between
pretty cool.
Two clients. Yeah.
Of course it is.
I think there's there's a Frankfurt to London something optical that was a big deal a while back.
Yeah. Today it's probably standard. Yeah.
Sure.
Now, one part of the infrastructure, and I have to change the topic here to space lasers. So I'll preface it with that because it's
Because why not?
of course. So we talk about all these different ways that we're trying to transmit information, and over time we've been finding faster, better ways to do it. Whether it was smoke signals, telegraphs, copper wire, wireless electromagnetic transmission. Now optical with laser with light, etc. Do we see another evolution of the optical's technology and maybe a different medium other than fiber? Is there a way to use light in a kind of a free space to transmit data, or is that too difficult today?
It works, and it's in use. There is like in RF technology, you have links between two optical transceivers, transmitters and receivers that are using open air communication. The problem with that is that it's easy to disturb. Fiber, you can bend, you can wrap, you can put into ceilings, you can put into underground, let it go through waters, through rivers, oceans, and the material it's made of is silicon, so silica, quartz, something you find on every beach. Unlike copper, which has now a supply problem and is increasing in its price ever and ever, the basic material that fiber is made of is cheap.
We have a lot of sand.
That makes me believe that this will persist for a while. We will find more sophisticated ways to use fiber. Today we have a single core, a 9 micrometer core within a cladding that has a different refractive index to guide the light in it. People are experimenting with crystal fiber, multi-core fiber, all ways to allow multiple transversal modes to propagate along the same fiber. That's another way to increase the reusable bandwidths. Will we see another medium? Well, we do it. Optics is, meanwhile, in many electronic devices, and there it would be waveguides, so-called waveguides, and that can be structures that are built into small wafers or wafer sections, cubes, and also there you have a change in refractive index that makes you guide light along a certain path. So we can create structures, splitters, combiners. We can create filters, demultiplexers, multiplexers on wafers. And the latest technology is to combine that with active devices, with lasers and photodiodes. So then you're at a point where in order to get a certain distance on a chip, you better choose an optical connection than an electrical connection, because again, it might be easier to push photons that way than electrons.
Is crosstalk a thing? Like, if you run a really fast signal through a trace on your PCB, that's gonna start interfering with other stuff on your PCB. Is that a thing for optical?
Yes, it exists in optical too. Yeah.
Okay.
If something, say, doesn't refract 100% on the cladding and bleeds into another neighboring fiber, is that basically that version of crosstalk?
That's what you do when you do a fusion coupler, for example. You get two fiber
really
cores
cool.
narrow enough so that they couple over.
Okay.
Optical probing works that way. When
I don't even think about probing as an issue.
Optical probing, yeah.
So you go with the fiber tip on the surface of such a wafer, and you get close enough so that there is optical coupling between the fiber or the tip and the structure in the wafer. That's the way you test these things before you break them into dices.
Wow.
Now, I mentioned space lasers because I always just assumed that, I'm going to keep saying it, I just assumed that
It's
optical...
better than the shark laser proposal from last time.
Yes, well, thank you.
Seems a little more practical.
The shark laser idea was great, but I guess this one is a little bit better.
It's the greatest. Yeah.
So point to
We have the
point.
best shark lasers. Sorry.
So I'm thinking through the atmosphere would be tough because there's a lot of atmospheric issues to deal with. But the question is, in my head, I just assumed that was a thing already. Maybe it's not. But even if we had, say, point-to-point optical communication from, say, a couple of satellites, would that have any inherent benefits over just using our standard RF technology we use today?
If you are in the vacuum, yes, because you get 1.5 more speed.
Okay, so it's faster.
Speed of light in vacuum is to 300,000 kilometers per second. In fiber, we just get to 200,000, and that's because of the refractive index of 1.48.
So conceivably, we could find some sort of fiber substitute with a lower refractive hollow fiber.
Yeah.
So it's like a vacuum fiber tube.
Well, air is almost as good as vacuum, with the exception that there are some molecules that create problems in some wavelengths areas. But yeah, that's one of the experimental stuff that people do with fiber, with structured fiber.
Correct me if I'm wrong, but the way fiber works is that the interface between the fiber itself and whatever's coated in, it has such a high refractive index that the light kind of just bounces its way through.
Currently, fiber has the refractive index in the core is higher than in the cladding, which guides it, which guides the light in the core.
So a hollow fiber would be like a mini mirror tube.
Yeah.
Okay.
Yeah, hollow tube.
That sounds pretty cool too.
I guess my last question would be, it's kind of similar. Maybe I'm rewording it here. You said there's a lot of similarities from protocol is the right word, like a physical layer standard between RF and optical, right? Mm-hmm. We're talking about the amplitude modulation, the quadrature modulation, techniques like that. If we had similar mediums and similar transmission speeds, are there any advantages between kind of the standard RF spectrum and the optical spectrum from a data transmission standpoint? Or are you just using a different carrier frequency and it doesn't matter?
Look at the Wi-Fi signal you have at home. You're choosing 5 gigahertz because it's less cluttered, but also 5 gigahertz gives you more transmission speed. Yeah, and I think that's a general rule. We're talking about a carrier that has 194 terahertz. Higher carrier frequency means you can modulate faster, theoretically. But it also means that there is more loss, attenuation, and dispersion.
Right.
Yeah, that's the downside of it.
Oh, okay. So that becomes harder to do then in free space versus a controlled channel like a fiber. Okay.
That makes sense.
Yeah.
Can I shift gears completely here? So we're talking about infrastructure.
It's your show, bud.
Yeah, right. We wanted to go.
Hardly. We're talking about infrastructure as a whole. How does technology trickle out? So I imagine there's this core of, like you talking OFC 64 was the buzzword, and is that a like internal network center to network center type thing, and that slowly works its way out until we have home optical routers or something? Or
in fact, it's that way. And the starting point is usually that leg of the network that has the most congestion. So we had the issue that the long distance was running out of bandwidth.
Okay.
And we say bandwidth doesn't mean 100% used. So there is a lot of headroom that the telecommunications service providers have and use to make sure that they have enough of reserves. So I think they start to scratch their heads at 20%.
20% of usage or 20% of headroom?
Of usage.
So 80% headroom.
70 to 80% headroom used to be, at least when I was in this, connected to that kind of business.
I'd like that kind of
5 to 10
margin
years.
and other things like, honey, I'll be home in 1 to 8 hours.
It depends. Sometimes it's good to do that.
It's true.
So it's the congested part of the network that drives the change.
Okay.
Currently, we have a different thing. Think of the big data centers that companies like Facebook, Google, Netflix are building. And that they're increasingly building in areas where they have cheap water,
Right.
cool water.
Yeah.
Because cooling is important, and power supply is important. So most of these things have, meanwhile, a power plant nearby. The recent trend is to go away from these mega data centers into distributed data centers. So the cloud is actually becoming a cloud of data centers as well.
Dispersed computing. It sounds
and
episode
dispersed
3.
Well, yeah. If you're ever browsing the web and say looking at a great example is if you look at the URL of a photo hosted on Facebook, you'll see the acronym CDN somewhere in the URL, Content Distribution Network. So they actually do this. It sounds like they're distributing it more. But if, let's say, you live in Russia or something and you're trying to access Facebook, it's not going all the way to the United States to fetch a photo and then send it back to you, right?
Sure.
There's some sort of local hub in Russia that it pulls from.
That makes sense. As opposed to, like, I know I had a friend who worked for Microsoft at one point in their Hotmail division, and part of your Hotmail account URL, when you went to that URL, had a server denomination. And it was like physically they could walk up to the server that had all your email information and say, it lives here. But I imagine that's
They must
since moved to more of a cloud
they
dispersed computing network thing,
have multiple copies of it.
which we also talked about in a previous podcast episode.
multiple
Go
copies.
check it out.
And this, the breaking point here is the level where you decide how you distribute that, or how you break a big data center into small pieces, is actually power consumption. So we're talking about 20 megawatt. That was learning of the recent show here in OFC in Los Angeles. You don't talk about a data center by its physical size or by its data capacity or by the data it crunches every day. It's the megawatt of power it consumes.
And that tells you how much.
That tells you how big it is,
right?
roughly. Yeah, it's
Interesting.
related to the computing. There's no direct translation to it, but this is the denominating factor. How much power does it take?
Wow.
And here is why we see distributed data centering. And now the communication infrastructure comes into place, because you're making an example to search for a picture. Okay. Now, most of that search is actually in and between the data center components. It's not that you are going through a list of servers and a list of addresses. It's you're sending a request, and then inside the data center, there's all of a sudden a lot of traffic related to this one request that happens between the data center elements. It's servers, it's storage, area networks, and so on. And this inside the data center traffic is taking up, if I'm not totally wrong, about 75% of the data center traffic. It's really internal traffic. And
it's just like keeping shop and cleaning house almost.
Searching.
yeah. Searching, grooming,
That's
whatever.
pretty cool.
And then
And sad.
if you distribute,
Hot, probably. It's probably pretty hot. Sorry.
All right,
If you
yeah.
distribute it. Yeah.
and if you distribute networks, if you distribute data centers into multiple smaller data centers, you have this traffic to go between them. It's a mesh network usually, and even inside the data center, we see now mesh networks. There used to be a hierarchical structure, server, top of the rack, and connection between the top of the rack switches and so on. And this is more and more a many point to many point connection, or a mesh type, matrix type of connection.
Interesting.
Which
an
is
amazing
good.
I had no
traffic.
idea. Yeah.
Good for the fiber optics industry, because that's a lot of business.
Now, something you mentioned earlier that jumped out at me, that might have jumped out at a couple of listeners. You said they start moving towards higher and faster optical links when they hit about 20% or 30% utilization of the fiber, correct?
Telecom people, yes. That's where they start scratching their head.
Yeah, so it's kind of funny to think like, oh, that's a really low number, but it's actually a pretty common number too in common serial buses as well. Mm-hmm. So the CAN bus, for example, is really popular. Around 25-30% bus load is like, okay, we're getting to be too much. But that's mostly because there's a lot of safety critical things going on inside that particular bus. What is the reason why they don't feel comfortable pushing the utilization rate higher in fiber?
They do, but simply not on the telecommunication links where they have a contracted, what's that called, quality, 5 nines, for example, 99.999% availability.
Uptime guarantees. Yeah.
Contracted uptime. Yeah.
Okay.
On the Datacom
That's
side,
almost exactly the same thing as a CAN bus, right? Like in a car, you want your airbags to go off, your automatic braking systems to work, your everything to function in that critical point in time.
Yeah, it's probably not peak 30%. It's average 30%. Is that the idea? Okay.
Yeah,
Okay.
yeah. On data centers, they would certainly go higher. I would be surprised if they started to be concerned at 20%. Yeah.
Interesting. We're out of time again.
Do you have any final questions?
I think I have so many questions, but I think, in the interest of time. You?
No.
Okay. Awesome. So Stefan's going to travel at the speed of light back to Germany, and
Can you believe he's came all the way out here 3 times now in the last month and a half to visit with us, and wearing, we're all wearing the same thing every time. It's a
thing.
It's interesting.
Some of us do that every time anyway. So anyway, so if I'm really excited to have had you here for these episodes, and I really appreciate you coming out.
It's fun.
If anyone out there is actually testing and working with optical devices, we'll definitely put a URL in the description. Are there any specific app notes or anything you'd like to point people to off the top of your head?
There's a whole host of app notes, but I think the best thing is to just check the subdomain, and that's www.keysight.com/find/OCT. That would be optical component test.
Awesome. We will put that in the description of the video and podcasts, and it's time for predictions. So, Hoffman? Hoftron, rather.
Didn't I hint on my prediction earlier? Can I just reuse that? What was it?
If you can remember it, then you can use
So
it again.
I'm so out of optical predictions. Let's see here. You want to go first? Give me a second.
Sure.
Yeah. Passing the buck.
Yeah, let me think about that. Who came up with this predictions idea anyway? That was
Probably you.
Can it be another space lasers prediction? I don't know.
Yes.
No, I think the dispersed computing side of things is going to transfer over more to the consumer side of things. So instead of one central hard drive on each person's computer here, instead all our data will be managed by some sort of internal Keysight company server. We see that a little bit now, and we're starting to get there with Exchange servers and that type of thing. But I think the size of the hard drive in your laptop will matter less than your internet connection to your local network connection.
Yeah, that's one thing. Then if you ever experience data loss, you're much more open to
Yes.
distributed backups and
That's for sure.
data in the cloud than before.
Absolutely.
Guess my prediction will be
Data sharks.
Sharks. More sharks. Within our lifetime, optical home networking.
Yeah, that'd be pretty cool.
Data rates will, as videos become higher and higher quality, internet speeds become faster. Like maybe we'll see optical links in the home as opposed to Ethernet.
That's why your Ethernet cable lights up when you plug it in.
Oh, is that a fiber line? Just shooting right out of the back of the computer?
Rainbow communication. That'd be. Anyway, we did talk about colors, so theoretically, it's kind of thing. Okay, we're definitely way out of time.
Do we have a prediction here?
Yes, I'm sorry.
Oh,
I
forget
skipped
our
Mike
guest.
a couple weeks ago, and I had to.
I'd say by 2020, I'll have a data center in my network wherever I live.
Ah, okay. 2020.
2020. Oh. Are you buying a data center?
No, I would just say I live next to one. Did I say network? No, neighborhood.
Oh, that's an interesting idea. Like a local,
neighborhood
like a
data
little
center.
data bank, local data bank.
There will be so many. You can hardly live anywhere without being in the neighborhood of a data center.
That is an interesting idea. You got local supermarkets, banks, data center. Going down to my local data center, pull a download of my emails.
Let me write you a data bank check, and you can.
Pay with Bitcoins.
All right, let's get out of here.
So thank you for watching. Make sure you subscribe to the Keysight Oscilloscopes YouTube channel. If you're testing optical devices, check out the link in the description and the one he described earlier, find/OTC. Is that right? OTC? Optical?
OCT.
OCT. Octal. OCT.
Optical
Okay.
component test.
Optical component test. That's a mouthful. I'm rambling now, so we should end. I'll see you the second and fourth Thursdays of every month. See you next time.
Thank you.
Recording in 12-bit RAW, by the way. But that's all. Okay.
So you can see all my pimples or what?
Oh my God. You didn't tell me that.